see the Google Meet screen. Okay, it's recorded now. All right, so we shall start now. Right. Okay. So last 2 weeks, okay, after the holiday break, before the holiday breaks, we have gone through chapters called root locus technique. Okay, so this is a continuation of that particular chapter, so the slides will continue from there, right? And this is where we have gone through previously. Okay, we have discussed about there is a possibility to test any point on the S-plane, whether it is a root locus or not to a system, right? So how to do the test? Okay, we have these two criteria, okay, where we know that the KGH should be equals to 1. Okay, so when we rearrange, then we have these equations, and then we also realize that in order to satisfy these conditions, okay, we have a polar system where the angles, okay, should be equals to 2k plus 1, okay, multiplied by 180 degrees. Okay, so this is just a rough ideas of how we can test, okay, any point, okay, in our S-plane, okay, whether it is a root locus point or not, right? So after that, we also quickly briefly go through how to sketch the root locus, okay, by identifying the number of branches, okay, the symmetry lines, okay, where is the intersections of the symmetry lines, okay, the real axis segment, okay, then the start ends point and the behavior at the infinity. Okay, so we just roughly see the branches, okay, depending on the number of pools. Okay, so if we have 2 pools, then we have 2 branches, okay, obviously. And then the symmetry would mainly depends on the locations of the symmetry points. Sometimes you will see that it will converge to the symmetry lines. All right, then the real axis segment is referring to the real axis, okay, where during the real axis, when we do the testing, we realize that the root locus will always occur from the start, okay, from the start point, okay, regardless of maybe zeros or pools itself. Okay, it will start from this point, okay, and then move to the next one, right? Any points before that, okay, the root locus will never exist. Okay, so we can see that we can segment it, okay, along the real axis segment. Okay, so we have this segment, okay, the first 2 point, okay, we have one real the root locus, okay, lies along this direction, these positions, and then this segment will be no root locus, and then the second segment, okay, so it will continue, okay, depending on the number of pools and zeros lying along the real axis. Okay, then from there also we can realize that, okay, usually the root locus will start, okay, from a 0, and from the pool, and then slowly move to the zeros. Okay, so this is the directions, okay, of the root locus, right? Then from there also we have this behavior at infinity. Because of the asymptote itself, okay, we can roughly estimate, okay, the location of the intersections, okay, the real axis intersect, okay, so this is the real axis, the sigma, okay, intersections point. So we can estimate by taking the summations of pools minus the summation of finite zeros divided by the number of pools minus by the number of finite zeros. Okay, then also the angle of the asymptote can be estimated by these equations, right? So we have this 5 starting points, okay, to sketch the root locus. Okay, so today's we will go through an examples, okay, to see how we can actually apply all these 5 points, okay, to quickly sketch a root locus for this particular system, right? So for sure, when we see this is a closed loop transfer functions, therefore we can just first thing first, okay, plot the pulls and zeros. All right. So draw your real axis and the imaginary axis, label them properly. Okay, real axis, imaginary axis. Then from there, okay, what we can do is that identify all the pulls and zeros, right? So we can have the pulls at 0, -1, -2, and -4, right? Okay, so you just draw 0, 1, 2, and 4. Then here we have 3, the 0. Okay, so the 0 is 0 point lah, all right? It's the circle point. The pulls we just put a cross over there, right? So we have this pulls and zero being plotted over here. So now based on our understanding, okay, we can know that the real axis segment, okay, the real axis segment, we know that the root locus will occurs at this segment, okay, and this segments, and this one they don't have a pair, right? So eventually they will go somewhere else lah, to the infinity, okay. Otherwise we have this, okay, and this one is pulls to 0, so immediately we can draw in this way, right? So very straightforward, okay. But this one we are not sure where it will go, right? So we can have some guesses, okay. Now the directions of a few segment over here, okay. So next would be to maybe probably we can identify the asymptotes, okay, the real axis as intercept, as we have seen previously, okay, the rules number 5, okay, infinities, okay. So we can estimate or obtain the real axis intersect, okay, real axis intersect by summing all the finite pools. So we have 0 plus -1 plus -2 plus -4. So we have 0, -1, -2, -4, right? And then minus the summations of all the finite zeros. So our finite zero would be -3. So -3. So eventually we get 4, -4, sorry. Okay, divide by number of finite pools minus number of finite zeros. So how many pools we have? 1, 2, 3, and 4. So we have 4 minus 1 pools. So 1 0, sorry. 4 pools minus 1 0. So we have 4 minus 1. So we get 3. So from this, we have estimated that the intercept for our asymptote will lies at -4/3, which is roughly over here, right? Okay, so this is -4/3, right? So from this, we know that there is a asymptote, okay, passing through this point, okay. And what is the angle of the asymptote lines? We can again estimate using these equations. That is 2k plus 1 multiplied by the pi, which is 180 degree, divided by this lah, right? The numbers of pools minus the number of zeros. So we have same 3 over here, right? So we have 3, okay, divide by the first one. We will start with k equals to 0. So k equals to 0, okay. 0 means 1 pi, so we get pi/3, okay, when k equals to 0, okay. So this referring to pi divided by 3 means 180 divided by 3, 60 degrees. So we can estimate a line which is 60 degree, right? 60 degree, right? Or maybe pi by 3 lah, right? Then the second one would be when we put 1 over here, then we calculate, we get 3, right? 2 times 1 plus 1. So 3 divided by 3 is we get 1. 1 times pi, we get pi. So pi is 180 degrees. So we get another line would be 180 degree. Okay. Then the third one would be here lah, right? So sorry. So eventually we can see that it is equally spaced. Okay. So if we continue to increase the number of k, okay, you will see that it keep repeating at these locations, meaning to say there is only 3 so-called asymptote lines. Okay, so what we can say or get used or get some informations out of this is that from these asymptote lines, okay, we can, sorry, yeah, I think just ignore the line that I draw, okay? Just refer to the blue dotted line, okay, which is more accurate, okay, 60°. So based on that, we would notice that the, let me erase it first. Okay, so roughly like this. Okay, so now based on this, okay, we can see that first segment, we know that there is something over here, right? Okay, some lines over here. Okay, then second segment is this one. Okay, means from the poles to the zero. So this one is along this asymptote line, so meaning to say this one is correct. Okay, then but however for this point, okay, since it is in these directions, nowhere to go, so it will go along this asymptote line, right? So eventually when you draw, okay, so we would see that the first segment, okay, we have roots locus along this, okay, but then since there are pools to pools, so they will go to infinity, right? So they will meet together, okay, at the middles between these two pools, and then they start to separate and go along the asymptote line, okay, towards the asymptote line, towards the infinity, right? Then for this point, we do not know where it will goes, right? There is no zeros to sink it, right? So to absorb it, so called. So in this case, they will go along the so-called infinity line. So you can see that because we know that the pools will goes to the zero, okay, meaning to say we have three pools without zero. Therefore, there is a three asymptote lines to define the directions of uh, the root locus. Okay, so eventually we have been able to draw this out lah. Okay, so we have the blue line. Okay, so it will go usually when you start from this point, go to the right, and if they meet in this point, then it will go down, okay, the other one will go up, right? Then for this one, go straight, okay, and this one goes straight, okay, for these cases. Okay, so this is how we can quickly sketch the root locus. Okay, next would be how we can refine the sketches, okay, by putting more details. Okay, sometimes from this point, okay, we can notice that there is a intersections with the imaginary axis. Okay, and also this point where it start to separate, okay, we may want to estimate where is this point may occurs. Okay, so based on these two particular points, so remember what is the characteristic of this is where it start to separate, right? Meaning to say this is the critically damp condition, right? Okay, so sometimes we may want to know what is the K or what is the values over here. Therefore, all these points may be useful. And also when it start to intersect with the imaginary axis, okay, meaning to say, as we know, when the root locus start to shift to the right hand plane, okay, the positive real axis value, it the system will become unstable. So we try to avoid, okay, any root locus which is on the right hand plane. Okay, so from this plot itself, we can know, okay, whether or when or the range of k values that you can select, right? So you have to identify these points lah. Okay, so these are the points where we have some interest there, then therefore we say we want to refine the sketch. Okay, so those points we call it as a real axis breakaway and break in, as well as the uh, j omega axis crossing. So this one is the intersect of the imaginary axis, whereas this real axis breakaway and break in points refer to this lah. Okay, this point. Okay, break away meaning to say this root locus is going away from it. Okay, so break away. So if it is break in, meaning to say it will go somewhere, okay, then come in, okay, come in and touch the real axis again. Okay, so sometimes at certain range it become not stable, and then it becomes stable again. We may not know. Okay, this is why we have to sketch the root locus for us to have a whole ideas, okay, on where or what we can select, okay, from the root locus technique itself, right? So we have the real axis breakaway, break in. Okay, so this one, okay, or all these things can be actually uh, roughly obtained from, again, these rules, okay, because we can test, okay, where is the point, right? Okay, so therefore we use the similar concept. Okay, we just use the kgh should be equals to this, and so we have the kgh equals to 1. Okay, and this can be represented by the pull length and the zero length lah, the cross, the multiplication of all these lengths itself. Okay, so how we can use that, okay, or how we can refine it. Okay, the first thing we would look into it would be the real axis breakaway and break in point. Okay, so we can see that break away meaning to say it touch together and then separate, right? So break away from the real axis, and then in these cases, okay, you will go back to the real axis again. Okay, we call this as a break in point. Okay, and then go to the zero lah. So in coincidentally here there is a zero, but then it's far away, right? So let me check if we can zoom in. Okay, we can't. All right, so never mind. So maybe later you can check the slides again. Okay, zoom in so that you can see that we have two zeros over here. Okay, immediately we know that the root locus will move along this segment. There is two pulls over here, the root locus will move along this segment. Okay, but then because there is no zero, so it will break away and then break in and go to the respective zeros. All right, so here the idea is that when it start to break away, okay, when it start to break away, as we know, the k value will start from the poles. Okay, it will start to increase. Okay, as we say, it start move and turn, right? Okay, why we draw this direction is because it referring to the increasing of the k value, the gain value. Okay, so meaning to say, at this particular segment, this k value compared to the pools, this point will have the highest k or maximum k lah, I would say. So we have this statement saying that the gain at the breakaway point is the maximum gain found along this segment. Okay, so when it continue to increase, okay, so maybe probably here k is 0. Okay, then k over here, let's say, is 1. Okay, then it start to break away. Okay, then come back to here, probably when they meet at this point maybe 20. Okay, then it start to split again to the pools. Then probably when it start to split to the pools, the value is 25. Okay, so we notice that, okay, when it is breakaway, the k value at the breakaway point is the highest, the gain is the maximum. Then when it comes to the break in, the gain value, which is 20, is the minimum. Okay, before it start to split to the zeros, right? So this concept we will use it, okay, to calculate, to estimate. Okay, so how we can calculate or estimate? There are three methods. Okay, for sure, the first one, just use simulation software. Okay, if you if you give you the diagram lah, okay, which I have tried lah using the Scilab. Okay, I just plot it out. Okay, then I get that patterns. Okay, so we can use the root locus program. Okay, but why we need all this is to validate or make sure that whatever we simulate is correct. Okay, at the beginning. Okay, make sure that there is no mistake in putting all the numbers and syntax. Sometimes minus, positive, okay, multiply, we forget the star sign and so on. It will give you different answers. Okay, so the second method would be, we call it as a maximum and minimum value of gain. Okay, by knowing that, okay, how to find the maximum and minimum, we use differentiation knowledge, right? So we differentiate respect to the so-called real axis lah, the sigma. Okay, therefore we can find the maximum value and the minimum value, right? So how we can use that, okay? So what we do is look for the open loop gain equations, okay? This KGH, we call this as an open loop gain equation lah, because it comprises of the gain, forward feedback, forward transfer function, and feedback transfer functions, right? So by having this one, we just have to differentiate. So what we do is, here we take these examples, right? This example, this circle, okay? We start to differentiate, okay? So how to get the KGH from the equations or from the transfer function block diagram, right? Whatever it is, okay? We notice that the K is K, right? The G itself is this whole thing lah, right? Okay. And the H itself is this one, okay? So immediately we get this should be equals to 1. Sorry, minus 1. So what we do is that we differentiate respect to sigma, right? We differentiate, we assume all this S is sigma, then we differentiate respect to sigma. So eventually, first we rearrange, okay? We rearrange, okay? Multiply, put here and there, rearrange, and differentiate respect to sigma, okay? When we do the differentiations, how we can do it? Just differentiate as usual, right? Differentiate, okay? Using the chain rules, right? So eventually we get this value, all right? So if you are not sure, just quickly pick up the calculus book and just study, okay, how to differentiate this one, okay? So eventually we get this one, and then it should be equals to 0, okay, in order to find the maximum and the minimum value, right? So once you set this one, how we can get the maximum and minimum value, okay? We know that the upper part, the numerator part must be equals to 0, right? So we just solve the upper part, okay? Eventually when we solve this quadratic equations, we get the sigma equals to minus 1.45 and 3.82. So meaning to say, we know that this point is 1.45, okay, minus and 3.82 lah, right? So this is how we can obtain it. All right. The third methods would be, we call this as a transition method. Okay, transition methods, we will use these equations, okay? Summations of 1 over real axis plus the zeros, okay, equals to the summations of 1 plus sigma plus the pools, okay? So how we can see this, okay? We just use this as an example so that you can see how we can apply this one, right? So what we do, you just use 1 over sigma all the zeros, okay? What we have zeros is minus minus 3, sorry, plus 3, and also plus 5, right? Okay, our zeros. But here what we do is we just put it in, okay? Minus 3, minus 5. Okay, same thing over here, put it in, okay? Since eventually you will cancel out each other lah, right? So we have sigma minus 3 and so on. By having this, okay, just solve them, okay? Simplify it, okay, into this term. Then once you have this term, again, it's a quadratic equation. You can solve it, you get the same answer, right? So if we compare it with the results in the Scilab, okay, you just use these two tips, okay? Pick the point over here, okay? Zoom, 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 pick, okay? So you get roughly get is minus 1.453, okay? Because I didn't click the exact point, but roughly we know that, okay, the software have plotted the so-called correct values lah, okay? So same thing for this 3.817. So what we get 3.82. So yeah, it's good enough. Either you have round it up over here, or maybe you didn't click the correct point lah, because this just use your mouse pointer to click and get the values, right? So based on this, if it is very close, meaning to say the software have plot the correct correct line lah, correct point. Okay, so this is how we can validate the the sketches from the software, okay, before we use it. Okay, otherwise we continue to use, but we do not know whether we make any mistake or not. Okay, the second point, okay, or refinements that we are interested with would be the imaginary point. Okay, for this one we do not have any special technique, okay, to get this point. What we relies on would be the rough Hewitt criterion, right? So we just use this one, okay? Do as what you have learned to find the what the stability, the gain for the stability itself, okay, using the rough criterion, okay, rough Hewitt criterion, okay. Then from there you force rho of 0, okay, because you want it to be unstable, right? Okay, you force the row of zeros in the rough table to find the gain, right? What I mean by forcing it, okay, is let's take these examples again. So we have the transfer functions kgh itself, okay, open transfer functions. But for the rough Howitz itself, we have to use the closed loop transfer functions, okay. So make sure you distinguish these two, okay. So in order to find this one, you have to use the equations like given, right? Or maybe you just recalculate itself, okay. So you just use these equations, okay. You can plug them in so that you get the closed loop transfer functions, okay. Then using this one, draw your rough table, okay. So this one, when you group them up, is S2 is the highest, okay. S and constant lah, right? So we have k plus 1, 3 minus 8k, and 2 plus 15k, right? I hope no mistake over here, okay. So from this itself, okay, we can assume this is a row of 0, okay. We force a row of 0 because we know that by having a row of 0, there is a possibility of imaginary roots, right? Meaning to say it become unstable. That's why we have to force, we call it force lah, okay. Force a row of 0, we assume this is a row of 0. So if it is the case, then this would be equals to 0, right? So we get the k should be 0.375, okay. So if it is 0.375, what we would do, okay, form the even polynomials, okay, just like the rough tables or methods, okay. Even polynomials by having that, okay. So this whole particular characteristics polynomial, we put them in, put in the k value, okay. Eventually we get the s, okay, which is occurs at 0 plus minus j 2.355, okay. So meaning to say the intersections will be 0.2355 with a gain of 0.375, right? So that is how we can estimate lah, right? The next one that we may interested with is the angle of departure. Okay, so this angle of departure and later arrival, okay, is it's referring to the, how should I say, the root locus where it will goes lah, okay, the direction of it, okay. So again, we use the graphical methods. You may use a graphical methods, okay. What we do here is we assume a point, okay, of a root locus close to the complex pool, okay. You may have a complex pool over here, okay, complex pool, let's see, okay, over here, all right. We have a complex pool over here, okay, x over here, right? So in this equation, we may have 2 zeros, 2 pools, okay. So what we are doing now is that we want to know where the root locus will go, okay. We call that as departure, fly off, okay, from from this root locus, okay? Because you can see that in the real axis, we can easily draw lines like this. Okay, this is pull, this is 0, okay? We can know that this is the directions, right? But how about those in the spatial area, okay? This space, okay? Which consists of the imaginary component. We may not know where it goes, right? Okay, this is where we want to know the angle of departure. Okay, we know that it will start from pulse and go to 0. So is it going this straight forward? No. Okay, it may go somewhere. Okay, it may go like this, or it may go like this. Okay, we don't know. Okay, so this is why we try to figure out the angle of departure over here. Okay, so how we can get that angle of departure is that, let me clear it off first. Okay, we just test a point very close to the pool, right? Because we want to go know the departure, right? The departure must be come from the complex pool itself. Okay, so we put a point close to it lah. Okay, just a point close to it. Okay, and then we start to draw all the lines. Okay, all the lines, okay, towards it. Okay, and test whether it is the so-called solutions of roots or not. Okay, so we assume that it is very close. Okay, and we assume all the angles are drawn and so on. Therefore, now we use these equations. Okay, so from this diagram itself, we can see that there is something very close, okay, which is minus theta 1, okay, then theta 2, theta 3, sorry, theta 3, okay, over here, theta 3, okay, theta 4, 5, and 6, okay. As you know, we just sum and minus, okay, according to the whether it is pool or zeros lah, right? So total them up must be equals to 2k plus 1 multiplied by pi or 180 degree. Okay, so this is the conditions. Okay, so we can readjust because we want to know the angle of departure, right? Where is the proper one. So this is an unknown. Okay, we rearrange this one by moving all this theta on the other side. Okay, so by having these equations, this one you can measure it, you can measure it, you can measure it, we can measure it, we can measure it. Okay, k you just change from 0, 1, 2, 3, or whatever it is lah, right? Then you will get all the values for theta 1. Okay, and that would be your angle of departure. Okay, so same concept for the angle of arrival. Okay, arrival would be where it comes to the 0. Okay, so again, assume something very close. Okay, same equations basically. Okay, because it's still relying to the concept of roots. Okay, so we test whether this is a roots or not, right? So it must comply with these rules. Okay, so eventually we have this same equations. You solve it, you will get the angles, okay, of arrival. All right. So from there, we can start to draw, okay, by knowing the angle itself, okay, by knowing the angle itself, then we can connect lah, okay, we connect from this departure to the arrival, right, based on the angle. Okay, so this is how we can plot and calibrate the root locus. Okay, why we need to plot and calibrate basically is to get some interesting point, okay, during our design later on, right? So we might want to know the exact coordinate of the root locus, for example, when it crosses the radial line representing 20% overshoot. Okay, we already learned that there is a relationship between the overshoot with the positions, right? With the so-called imaginary or maybe the radial lines and so on. So there is a relationship between all these things, okay, and how we can actually obtain it, okay, because we already have the root locus. We just have to draw all this line and get it, okay? Visually, we can see it visually. We don't, once we know that particular point, okay, then we can roughly estimate, okay, to help us lah to easily obtain the real solutions. Okay, so some point or sometimes or some points on the root locus and their associates can be obtained very accurate. Okay, if you draw it properly, then very accurate, right? So how we can get all these points, we again use this equation, the gain value k equals to 1 over gh, okay, which represent the product or the multiplications of all the finite pool lengths divided by the finite zero lengths. Okay, draw all the lines and just do it lah. Okay, so here is all the points that satisfy this condition as well. Okay, so here take this short simple examples like assuming 20% overshoots. Okay, maybe find an exact point where the root locus are at the 0.45 damping ratio. Okay, so what it means by 0.45 damping ratio line, okay, and the gate at that point. Okay, so first we have to find what is the angle related, or what is the damping, yeah, what is the angle related to this. So we know that from chapter 4. Okay, you just refer back. Okay, the damping ratio should be equals to the cos theta, okay, the angle of this. Okay, so we know that the the damping ratio is 0.45. Okay, so therefore we get the so-called line, this so-called red dotted line would represent the damping ratio of 0.45. Okay, 0.45. So we can now get the exact so-called specifications, okay, that we require. Sometimes the system, we say we want to improve the system, maybe from damping ratio, maybe from zero, no damping, we want to improve it to a certain values. Okay, for example, in this case, we have a specific point we are desire with, okay, 0.45. Then from there, we draw a line, okay, and that red dotted line, if we zoom in, okay, I zoom in, okay, you can see that it is crossing this root locus, okay, this root locus, all right, the blue line itself, okay, and that blue line actually is equals to 0.566, okay, 0.566. Okay, so you can use all these conditions to get lah, okay, the exact k value. Okay, so how to get this one, you may have to try it on your own. Okay, if I explain, you may still not get it because it still depends on this concept. Okay, you just have to try, pick up your pen, okay, try to calculate the k, okay, and this angle, right? So once you pick up your pen or pencil to try this, okay, by measuring the length, okay, how to measure, you can use the Pythagoras systems, okay, to measure all this length by the angle, right? So this one I just simulate using Excel, all right? So by doing that, okay, I can get, okay, the exact point, okay, that satisfy this condition, minus 180 degree, and we know that at this point, this is the position of the root locus, okay, and that is referring to the radius of 0.566. Okay, so it's the radius of this is 0.566, right? So just use some try and error. Okay, since you already have the sketch, right, you can try with different point lah, right, accordingly, right, to evaluate their angles and locate the points accordingly, right? Just pick up your pen or pencil, try any points you want, all right, then you realize you may not get the angle equals to minus 80 degree. Okay, only when it is equals to minus 80 degree, then that is the position of the root locus and it hits this point. Okay, and we know that that is the point that that intersect, okay, with this damping ratio 0.45, right? So that is the try and error, okay, because along this line, okay, you can pick many points, okay, this red dotted line, okay, and it cross like this, okay, this blue line cross like this, okay. So there is a lot of point, and you do not know exact point. This is where I just try lah, okay, pick nearer again, so eventually I get this radius, okay. I want to know what is this radius. This is the concept lah, right? So you just have to try it on your own, right? Okay, so how we can use that for our design purpose, okay? So one of it is to increase or maybe to obtain a desired transient response, okay, by adjusting the gain, okay? By adjusting the gain is the most common or basic control methods lah, okay? You just adjust or increase or decrease the K value, all right? So that it happens to meet your desired specifications, right? So in the previous sections, we say that we want the 0.45 damping ratio line, okay, and we found that the gain is 0.93, okay. Eventually, we found that as 0.93, okay. So the questions may come in the way like this question is the designer questions, okay. Someone will ask you, or yourself asking yourself, okay, you asking yourself this question, okay, after you get this value lah, right? Does this mean that the system will respond to 20.5% overshoot, okay, because the damping ratio is 0.45, so you may ask all this maybe stupid question or whatever it is, okay, but it will let you start to think, okay, whether it's correct or not, okay, because whatever you estimate, we're still doing some estimations, because the theory part, okay, may not be able to capture or suit for so-called higher orders system, okay. We still relies on maybe polynomial systems and so on, so we have to do some questioning lah, okay, whether it's still valid or not and so on. So here what we can say is that the formula describe the percent overshoot, settling time, all these things are close to the two closed loop pools and no closed loop zeros. Therefore, we can justify that even though it is a higher order pools, okay, or higher order system, the response itself for the higher order does not appreciably change the transient response, okay, because it's very close to the pools itself, okay. And also we can say that the closed loop zeros near to the closed loop second order pools, okay, that will cancel out the effect lah, right, and so on. So this will eventually justify why this estimation can be acceptable lah. But still later on, since we nowadays we have computers, okay, simulation software, after you get the K, you just put it into your Xcos or Simulink to simulate it, okay, very straightforward, okay. Previously we may not have this opportunity to quickly do all these things, therefore we have to justify whether it's right or wrong and so on, okay. So all these justifications will improve our understanding with the system, and at the same time, as I say, computer still depends on your input, so all these specifications will allows you to check, quickly validate your sketches, okay, in the computer or simulation in your computer, right? So here is a procedure for higher order system, okay, meaning to say more than second order, okay. So we still do the same thing, sketch the root locus, assume the system is second order, okay. without any zeros. Okay, find the gains. Okay, justify. Okay, this is where the justification is required. Okay, justify whether it is a second order assumptions or not. Okay, and if the assumptions cannot be justified, then perform the simulations. Okay, meaning to say put into the simulink or xcos lah, right? But nowadays you can just skip this. If you are in front of computer, you get the k value, just simulate it, right? It's very straightforward. All right. So this is how you can do it, right? So why or how we can say that is that from this figure, okay, figure B, okay, figure D, okay, figure B will have a better second order approximation than figure A, okay, because the closed slope pool, okay, P3, closed slope pool P3 is far from the dominant, okay, dominant pool, the one that are closer to the origin, okay, to the closer to the to the origin, okay. So the further it is, then the better approximation it is, okay. So this one is closer to this, okay, then we may not say it's good lah, okay. But if it is far, the P3 is far away, then it is better, okay. So this is how we can say the dominant pool is this one, okay, the one that you draw for your pools and zero, okay, the black color dot, okay, the blue line is the one that the root locus lah, the one that you are going to select, okay. That's where you may when we select, then we may start to ask whether it's still correct or not, okay, and so on. So the further it is from the dominant pole, then yeah, the better approximation of it, okay, the P3, okay. The second one would be the figure D would yield a much better second order approximation than the C, since the P3 is closer than the cancelling zero, okay. P3, okay, P3 is closer to the cancelling zero, okay, either away from the dominant pool or close to the zero lah, because we can see that this is the direction of the root locus, okay, from this root to the zero, okay. In this case, there is a pools and zeros, right? So the further it is towards the zero, then the approximation of second order is better. That's all, right? So this is how we can somehow justify lah, okay. But then still the best way, do the simulations, right? Here is an examples of identifying or design, okay. We start with a little bit of design before we actually look into the design of compensator, okay, which involves the integrator and the differential lah. Now K, the gain, represent the proportional, okay. The P, the basic, just change the K value, right? No other values over here. Then yeah, so this would be the easiest design that we will deal with for now, okay. So consider this system, design the K value or the gain value that will give us 1.52% overshoot, okay. Then from there we just estimate the settling time, peak time, and steady state error, right? So what we do, yeah, you can try it, okay, without using the software later on, right? But here for our examples, we just use software over here first. Sorry, I hold on. Okay. For this, what we can do over here is that what we see here, there is a breakaway point. Okay, there is a break-in point. Okay, breakaway point and break-in point somewhere very close over. Breakaway and break-in point. Okay, so what we would see, okay, in order for us to get the K value near to 1.52%, okay, we have to draw something lah, something similar to this. Okay, we draw the line. Okay, which represent that particular so-called items lah, okay, or specifications, okay. So assume that it can be approximate using the second order undamped system without zeros. Okay, so what we would do is that 1.52% overshoot is equals to 0.8 damping ratio. Okay, so how to get that one? You just use this equation. Okay, again, you have seen this in the previous, I think, time response chapter. Okay, where we have estimate the percent overshoots. Okay, that equations that relate to the damping ratio, right? So use that percent overshoot and solve this. Okay, in order for you to get the damping ratio. So eventually, when I solve them out, is 0.8. Okay, so if it is 0.8, then from the Scilab, okay, we can draw the pools and zero, the root locus with the damping ratio line. Okay, so it's very straightforward. So therefore, you just draw that particular line lah, so that you can see the intersect of all these points. Okay, once you see all these intersect point, what you can do in Scilab, okay, use the pick point, just go into it, click, okay, you can get the K value. Okay, very straightforward if you have the software. Okay, but when we do not have the software, what we will do, we just do the try and error, right? Remember, try and error, you just need to use the kgh equals to -1, and also to make sure that the angles of 2k plus 1 multiplied by 180 degrees. Okay, yeah, that is the things lah. Okay, so that is the concept of getting all these points. That's why I previously I asked you to just get a pen and try. Okay, to test all these points, right? Just as long as you can identify that particular point, then it's good enough. Okay, you already know the concept, then you just use the software later on once you know the concept, right? So from there, we may get 3 points that satisfy this condition, that cross this damping ratio line. Okay, 2 is at this so-called circle lah, right? And then the another one would be at this splitting, right? So if you zoom in later, you will see it clearer. So this 3 point would be this point, and this point, which have a different K value. Okay, 7.38, 36, 12.79, and 39.62, right? So now what we would do, okay, would be to check, okay, which one would be the proper one lah. Okay, so as we expect, okay, as we expect previously, we say that the further it is towards the zeros would be the better one, or maybe the one more away from the so-called pools would be the better one, right? So meaning to say, the higher the K, the better it is lah, right? In short, all right. So what we can do is now we test each of this pool. Okay, this closed slope pool represent this point lah. Okay, this red dotted point. Okay, so we test all these points and find what is the settling time, peak time, and the steady state error. Okay, why we use KV? Just check back the dominant pool lah. So this one, the system type is 1, so we use KV, right? Okay, to get the steady state error, right? So this is why we use KV lah, right? Not KP and KA, right? So use all this equation to evaluate all these things. Okay, we realize that since there is a closed loop pool which is -1.5, okay, at the real axis value, so therefore we have to double check again, okay, whether this third pools is a valid one or not, because we assume that this system is a second order system, but we have more than that, right? Okay, so we will calculate the locations of this, okay, and check these so-called three values. Okay, then using the root locus program, search the negative extension of the real axis. Okay, between the so-called minus 1.5 and the pool minus 10. Okay, that match the gain found in this particular things lah. Okay, and for each we would check, okay, to get the damping ratio, the pools, and so on. Okay, and here is the location of the third pool. Okay, location of the third pool, right? So what it means here is that for case 1, okay, when we select the closed loop pool to be in this way, okay, the third pool will occurs over minus 9 point, yeah, somewhere here, okay, 9.25, okay. And there is a second one for case 2. When we select this k equals to 12.79, it occurs over here, and so on, right? So these positions is actually represent thing, so-called, you can see that there is three pools, right? Okay, k equals 7.36, 12, and 39. Okay, so what happens is we try to locate, okay, where is the location during this segment, okay. For sure we have also this segment, okay, this one will move, okay, go, okay. We are interested with this, the so-called third pool, okay, third pool that are lying along the real axis, okay. So where is the location when k equals to 7.36? The third pool will be somewhere here, okay. Then the second pool would be somewhere here. The third pool would be somewhere very close over here, okay. So from these cases itself, then we may say that the case 1 and 2 will yield a third closed loop pool that are relatively far from the zero. Therefore, yeah, there is no cancelling effect, and these two pools may not be the a better one, or these two pools is the worst one, okay, as compared to the third one, okay, which is the green one, because the third one is very close to the zeros and very far away from the dominant pools, right? Okay, therefore we would say that when k equals to 39.64, this approximations of second order system would be considered valid, better, okay. So whatever we calculate over here, the first one and the second one, all this value, these assumptions of TS, TP, KV, remember this equation is based on the second order system, So this is why we say that whatever we get, we use second order system to evaluate the settling time, the peak time, and this value may not be correct, okay, may not be correct. And the one that we realize can be approximately good, okay, to the second order system would be this one, okay, the third one. Therefore we would say that this value is much better, okay, much closer to what we expect, okay, when we do the calculations, okay. For this one, it may far away from what is expected for the settling time. Therefore, sometimes whatever you calculate may not be correct in this way, right? Because they are approximations, okay? We approximate it, right? So we try to plot it out, okay? Okay, just comparing the second order curve and the third order curve lah, right? So if we have the software already, we can plot it out, okay? When we realize that at k equals to 12.79, okay, they are far away, okay. But when we are using the k equals to 39.64, they are much closer, and the settling time also very close, okay. This one, probably the settling time, you can see that this one already maybe settle over here, this one settle over here, sorry, over here. So there is a wrong approximations lah using the equations. However, using this k equals to 39.64, the peak time very similar, Okay, settling time very similar. Okay, and also for sure the steady state error also very similar, since the characteristics of approximation is there already, right? So this is how we can justify that the pools or the case number 3 would be the proper one. Okay, when we use the second order system to estimate for the settling time and the peak time. All right, so this is just to check, right? So any questions before we end here? Let's check if there is any questions. Okay, no questions so far. Right, so this would conclude the root locus technique. Okay, so we have studied from how to sketch the root locus. Okay, how to test any point on the S plane, whether it is the root locus or not. Okay, and from there also we try to use the concept of a second order system, because we only have second order system to estimate equations to estimate the peak time, the settling time, and so on. Okay, we use that to estimate. Okay, but then with conditions lah. Okay, based on the root locus technique, right? So I hope that you have learned properly from these slides, and just try to make sure you just try to check the k value lah. Okay, do the try and error. Okay, few points is sufficient, right? So if no questions, then we will end this sessions. Okay, and we will continue again tomorrow. Okay, with another technique called frequency response technique. Okay, frequency response technique. All right, so no, that's all from me. Stay safe and see you again tomorrow afternoon. Right? See you. Bye bye.
Thank you, sir.
Thank you, doctor.
Bye.
Thank you, doctor.